The oldest map ever drawn of the cosmos contains a wound that no one can explain. When scientists first projected the full sky image of the cosmic microwave background radiation, the ancient light left over from the Big Bang, they expected something close to visual static. Tiny, random temperature variations distributed uniformly across the sky. That is what a universe born without a preferred direction should look like. Instead, they found a region, a vast, impossibly cold patch of sky that refuses to fit any known model. And decades later, despite every technological advance and every recalibration of instruments, it is still there. The cosmic microwave background is not a photograph of distant stars. It is a thermal imprint of the entire universe, as it existed roughly 380,000 years after the Big Bang, when matter and light finally decoupled and photons were free to travel for the first time. Every detail in that map carries information about the structure and physics of the infant cosmos, which is precisely why the cold spot is so disturbing, because it is not supposed to be there. First identified by the Wilkinson Microwave Anisotropy Probe and later confirmed independently by the Planck satellite mission, the cold spot sits in the southern celestial hemisphere and measures roughly 70 to 150 microkelvin below the surrounding temperature. In absolute terms, that sounds negligible. In cosmological terms, it is staggering. The probability that a feature this large and this anomalous would appear by random chance in our theoretical framework is less than 1%. Statistically, it has no right to exist. Scientists did what science demands. When confronted with the impossible, they looked for the error. They recalibrated instruments. They modeled interference from interstellar dust. They tested every conceivable source of contamination. The anomaly did not shrink. It persisted, fully real, undeniably enormous. The most straightforward explanation involves a supervoid, an enormous region of space spanning roughly 1.8 billion light-years in diameter in the direction of the constellation Eridanus, containing dramatically fewer galaxies and gas clouds than cosmic averages predict. As photons from the ancient background radiation travel through this void, they lose energy climbing out of the reduced gravitational potential on the far side. This is called the integrated Sachs-Wolf effect, and it would cool those photons, producing a cold patch on our maps. The problem is the math. Measurements of the actual Eridanus supervoid confirm it exists. It is real. But even a void of this extraordinary size can only account for approximately 10 to 20% of the observed temperature deficit. The void exists. It simply is not empty enough to explain what we are measuring. Something else is responsible for the remaining 80 to 90% of the anomaly, and we do not know what. This has forced some theoretical physicists, including Laura Mersini-Houghton at the University of North Carolina, to entertain an explanation that sounds indistinguishable from speculative fiction. What if the cold spot is a scar? What if, during the violent inflationary expansion, immediately following the Big Bang, our bubble of space-time collided with a neighboring one? If two separate universes made contact in those first moments of existence, the impact would have left an imprint. It would have redistributed matter asymmetrically and left behind a region with anomalous properties, a cold spot. To be clear, this is not mainstream scientific consensus, but the mere fact that credentialed physicists must seriously consider it tells you everything about the depth of the problem. We are looking at a section of sky that flatly refuses to conform to our models, and the most complete explanation available involves something from outside our universe leaving a mark on the inside of it. If that seems difficult to accept, consider what happens when the same background radiation map is analyzed not for individual anomalies, but for overall statistical patterns. Because then a second problem emerges, and this one has an actual name that cosmologists coined in full seriousness. They call it the axis of evil. The cosmological principle, the foundational assumption underlying modern astrophysics, states that the universe has no preferred orientation. Averaged over large enough scales, every direction should look statistically identical. There should be no axis, no preferred alignment, no special direction that matter somehow knows about. When researchers analyzed the temperature fluctuations across the cosmic microwave background with precision instruments, they found a pattern. The regions of elevated and reduced temperature are not randomly scattered. They align along a specific axis running through the sky, an axis that corresponds almost exactly to the plane of our own solar system and to Earth's orbit around the Sun. Think about why that is so strange. The background radiation originated 13 billion years ago. It has absolutely no causal relationship with Earth, with our Sun, or with the orbital plane of our planets. There is no physical mechanism by which Earth's position in the solar system could influence the large-scale structure of the universe. And yet the data suggests the entire observable universe has an orientation centered on our location. Either something is deeply and systematically wrong with our maps, some unidentified contamination that preferentially aligns with the ecliptic plane, or the universe genuinely has a preferred direction. Copernicus devoted his life to demonstrating humanity does not occupy a special position in the cosmos. The axis of evil appears to suggest that at the largest scales we can observe, something disagrees. Before looking outward at the largest structures in the universe, it is worth understanding the scale of motion happening across it. In an expanding universe governed by standard cosmology, all large-scale motion should be dominated by expansion itself. Everything recedes from everything else, and at sufficient distances that recession constitutes the only significant velocity. In 2008, a research team led by Alexander Kashlinsky analyzed the velocities of hundreds of galaxy clusters and found something that violated this expectation entirely. The clusters were not simply participating in cosmic expansion. They were drifting together. An enormous river of galaxies extending across billions of light-years was flowing coherently toward a specific patch of sky between the constellations Centaurus and Hydra, moving at nearly 2 million miles per hour, independently of the universal expansion. Kashlinsky's team called it dark flow. Whatever gravitational influence is pulling these galaxy clusters must be vastly more massive than anything visible within the observable universe, but we cannot see it. We can only measure its effect. Part of this motion is attributable to a known gravitational anomaly called the Great Attractor, situated roughly 250 million light-years away in a region of sky obscured by the dense dust of our own Milky Way. We cannot observe it directly with optical telescopes, but we can feel its influence. Entire galaxy clusters, including our own, are being pulled toward it at hundreds of kilometers per second. The Great Attractor itself is now understood to be a component of an even larger structure called the Laniakea supercluster, a gravitationally bound network of 100,000 galaxies spanning 520 million light-years. Our entire local group of galaxies is a small suburb in this cosmic metropolis, and even Laniakea does not fully explain dark flow. The motion extends far beyond what local gravitational attraction could produce. The galaxies are flowing towards something outside our observable universe entirely, something so massive it can exert gravitational influence across cosmic distances we cannot even measure. Some astronomers propose it could be the gravitational signature of matter that existed before inflation, structures from a previous cosmic epoch stretched beyond our visible horizon. Others suggest it could be evidence of mass concentrations in adjacent universe bubbles in an eternal inflation scenario. The most sobering possibility is that we are detecting the gravitational pull of another universe, tugging on our matter through higher dimensional space. Dark flow tells us that cosmic expansion is not the only force shaping how the universe moves. There are deeper currents running beneath the expansion, invisible tides pulling in directions our models never predicted. Now consider scale. According to the cosmological principle, matter should be distributed relatively uniformly across sufficiently large distances. There should be a maximum size to cosmic structures because gravity has only had a finite amount of time to pull matter together since the Big Bang. Calculations give this a name, the cosmological horizon scale. Structures significantly larger than about 1.2 billion light-years across should not exist because there has not been enough time for gravity to assemble them. In 1991, astronomers discovered the Claus-Campusano Large Quasar Group, spanning approximately 2 billion light-years. Already beyond theoretical limits. Then we found the Sloan Great Wall at 1.3 billion light-years across. Then in 2013, astronomers confirmed the existence of the Hercules Corona Borealis Great Wall. It spans 10 billion light-years. 10 billion. That is roughly 10% of the diameter of the entire observable universe. Light would require 10 billion years just to travel from one end of this structure to the other. The structure is wider than the total time elapsed since the Big Bang would theoretically allow to have produced it. It simply should not exist under any reasonable interpretation of our cosmological models. And we keep finding more. The giant arc, discovered in 2021, spans 3.3 billion light-years. The Big Ring, confirmed in 2024, measures 1.3 billion light-years in diameter. These are not statistical edges of acceptability. They are far into the territory of the impossible, and astronomers are finding them regularly now, with better instruments and wider surveys. Some cosmologists have tried to explain these structures as chance alignments of smaller objects that appear connected from our perspective. But spectroscopic analysis confirms that the quasars and galaxies within these formations share common velocities and distances. They are physically real. The most radical explanation is that our understanding of cosmic time is fundamentally wrong. If the universe is older than we believe, or if gravitational structure formation occurred much faster than our models predict, then these formations become possible. But either option requires revising nearly everything in our cosmological timeline. We are looking at structures that point-blank contradict our best theories, and they are sitting in the sky defying us to explain them. Consider now the problem of time itself, as measured by the most ancient objects we can observe, the universe. According to our most precise measurements of the cosmic microwave background, is 13.8 billion years old. That number has been refined repeatedly and is considered among our most reliable cosmological measurements. The physics of stellar evolution is also very well understood. We know how stars are born, how they age, and how their brightness, temperature, and chemical composition tell us their age. When astronomers apply these techniques to the oldest stars they can find, particularly extremely metal-poor stars from the first generations after the Big Bang, they sometimes calculate ages of 14 to 15 billion years, older than the universe itself. The most famous example is the star HD 14283, sometimes called Methuselah. For years, its estimated age sat at 14.5 billion years, with an uncertainty of 800 million years. Even at the lower bound of that uncertainty range, the star was older than the universe. Revised calculations have brought its age estimate to approximately 14.3 billion years, but that still creates uncomfortable overlap with the age of the universe at the scale of measurement uncertainty. And Methuselah is not alone. Several other extremely metal-poor stars in the galactic halo show similarly problematic ages. Astronomers have been trying to resolve this for years. Some argue that stellar evolution in ancient stars must work slightly differently than we model, that mass loss or nuclear reaction rates in extremely metal-poor environments differ from laboratory measurements. Others wonder if the error lies not in stellar physics, but in our determination of the universe's age itself. If the universe were actually 14.5 or 15 billion years old, these stellar ages would fit comfortably. But changing the age of the universe is not a minor correction. It would require revising the entire standard cosmological model and ripple through every calculation of dark energy density, matter distribution, and the timeline of structure formation. The most unsettling possibility is that both measurements are correct, and something more fundamental is wrong. Perhaps stellar evolution in the very early universe proceeded through mechanisms we have not yet identified. Or perhaps the timeline of the Big Bang is not as linear as we assume. For now, the scientific community holds an uneasy truce, massaging error bars until they barely overlap. We are looking at stars our best physics says are too old to exist, and somewhere in our understanding of cosmic time, there is a crack. In 2023, the James Webb Space Telescope began returning images of the early universe with a clarity no previous instrument could achieve. Astronomers expected to see early, small, disorganized protogalaxies in the process of assembling themselves. What they found instead were massive, fully formed galaxies existing just a few 100 million years after the Big Bang. Galaxies that should not yet have had time to form. And at the centers of these impossibly early galaxies sat supermassive black holes. Not small stellar remnants, but monsters containing millions to billions of solar masses, fully assembled when the universe was barely 3% of its current age. Black hole formation and growth is a well-understood process in outline. Black holes form when massive stars collapse at the end of their lives. They then grow by pulling in surrounding matter and by merging with other black holes. Both processes take time, and that time is constrained by physics. The Eddington limit defines the maximum rate at which a black hole can accrete matter. Above this threshold, radiation pressure from infalling material becomes so intense that it blows away any additional gas attempting to fall in, cutting off the food supply. This limit means black holes can at most double their mass every few tens of millions of years under optimal conditions. Starting from a stellar mass black hole of 10 solar masses and allowing it to grow at the maximum possible rate for the first 500 million years of cosmic history, you might accumulate around 10,000 to 100,000 solar masses. We are finding black holes with millions and billions of solar masses in galaxies only 500 million years old. The numbers do not work by many orders of magnitude. Some researchers have proposed that these black holes did not start small. Perhaps they began as massive objects formed by the direct gravitational collapse of enormous primordial gas clouds, bypassing the stellar phase entirely. This process, called direct collapse, is theoretically possible but has never been confirmed. Others suggest that in the extreme density of the early universe, black holes could have exceeded the Eddington limit, feeding at rates our laboratory physics does not allow. The most radical explanation invokes primordial black holes, objects that form directly from density fluctuations in the first fraction of a second after the Big Bang, before any stars existed at all. If primordial black holes are real and sufficiently massive, they could seed the early supermassive black holes we are now discovering with the James Webb Space Telescope. The problem is that we have never directly detected a primordial black hole. We are proposing an unverified phenomenon to explain an impossible observation, and every new deep field image from the telescope makes the problem worse, not better. Every image reveals more impossibly early and impossibly massive structures. We built our best model of how the universe assembled itself, and reality is flatly disagreeing. Now consider the invisible architecture holding the visible universe together. Something is wrong with how galaxies move. This has been known since the 1930s, when Fritz Zwicky studied the Coma galaxy cluster and measured how fast individual galaxies within it were moving. The visible matter, all the stars and gas that could be detected, accounted for less than 1% of the mass needed to gravitationally bind the cluster. Either the galaxy cluster should be flying apart, or an enormous amount of invisible mass was holding it together. He called it missing mass. For decades, astronomers hoped they were simply missing dim stars or cold gas that detection technology could not yet find. Every improvement in observational capability confirmed the deficit instead. In the 1970s, Vera Rubin measured the rotation curves of spiral galaxies. In our solar system, planets farther from the Sun move slower because the gravitational influence weakens with distance. The same logic should apply to stars orbiting the centers of their galaxies. Stars near the outer edges should orbit more slowly than those near the center. But Rubin found that stars at the edges of galaxies orbit at roughly the same velocity as stars near the center. The only consistent explanation is that galaxies are embedded in enormous halos of invisible matter extending far beyond the visible disk. Matter that emits no light, absorbs no light, and does not interact electromagnetically in any way we can detect. We can only infer its existence from its gravitational influence on ordinary matter. We call this dark matter, and it constitutes roughly 85% of all matter in the universe. Everything we can see, every star, every galaxy, every planet, every atom in your body, adds up to only 15% of the matter that actually exists. The rest is invisible, intangible, and completely unidentified. We know dark matter is there. Galaxy rotation curves only make sense if it exists. Gravitational lensing, where massive objects bend the path of light from distant sources, reveals dark matter distributions independently. Computer simulations of galaxy formation simply fail unless dark matter is included. Remove it, and everything collapses. We know approximately how much of it exists. We know roughly where it is. We just have no idea what it is. For decades, the leading hypothesis was weakly interacting massive particles, heavy subatomic particles that pass through ordinary matter like ghosts. Physicists built enormous underground detectors, shielded from cosmic rays, hoping to catch rare collisions between dark matter particles and ordinary atoms. Decades of searching. Sensitivities improved by orders of magnitude. The detectors found nothing. Not a single confirmed detection. Alternative theories have proliferated. Axions, primordial black holes, particles from a completely separate dark sector invisible to us except through gravity. And then there is the most disruptive possibility of all. Perhaps dark matter does not exist. Perhaps gravity itself behaves differently than we think at very low accelerations. Modified Newtonian dynamics, or MOND, proposes that below a certain threshold acceleration, the inverse square law of gravity changes its behavior. The theory can explain galaxy rotation curves remarkably well, but it fails badly when applied to galaxy clusters and to the structure of the cosmic microwave background. Observations of gravitational lensing show mass-bending light in locations where no visible matter exists at all. The universe appears to demand the existence of dark matter, not just a modification of gravity, and so we remain in an absurd situation. 85% of all matter in the universe exists in a form we cannot see, cannot touch, cannot capture, and cannot identify despite decades of dedicated searching. We have mapped where it is. We have measured its weight. We just cannot find out what it is. If dark matter is strange, dark energy is stranger. At least dark matter behaves like matter. It clumps together, holds structures together, attracts other mass through gravity. Dark energy does something that violates every physical intuition. It pushes things apart. It accelerates the expansion of the universe. In 1998, two independent research teams studying distant Type Ia supernovae made a discovery that would earn them the Nobel Prize and fundamentally rupture cosmology. Type Ia supernovae explode with a predictable peak brightness, which makes them reliable distance markers. By comparing their apparent brightness to their expected brightness, you can calculate their distance. By measuring their redshift, you can determine how fast they are receding. Everyone expected to find that the expansion of the universe was slowing down over time as gravity gradually reined in the outward momentum from the Big Bang. Instead, the supernovae were dimmer than expected. They were farther away than they should be. The universe was not decelerating, it was accelerating. The expansion of space itself was speeding up. There is nothing in general relativity, nothing in our understanding of gravity, that would cause this. It is like throwing a ball into the air and watching it accelerate upward instead of arcing back down. Multiple independent measurements confirm the result. The universe is expanding faster now than it was billions of years ago, and the rate of acceleration is increasing. To account for this, cosmologists introduced a new term into their equations. They called it dark energy. They do not know what it is or where it comes from. They know only that it must exist, because otherwise the observations make no sense. Dark energy appears to be a property of space itself. As space expands, more dark energy comes into existence, which drives further expansion in a compounding effect. It constitutes roughly 68% of all the energy in the universe. Consider what that means for our accounting of reality. 68% dark energy, 27% dark matter, 5% ordinary matter, meaning everything we have ever observed, built instruments from, and thought about. 95% of the universe is invisible and not understood. We have a working model of only 5% of reality. The most natural physical explanation for dark energy is vacuum energy, the baseline energy residing in empty space itself. Quantum field theory predicts that even a perfect vacuum is not truly empty. Virtual particle pairs constantly flicker in and out of existence, and quantum fields fluctuate around their average values. This activity should give empty space a small but non-zero energy density. When physicists calculate what this vacuum energy should be from quantum mechanics and compare it to the observed value inferred from cosmic acceleration, the two numbers differ by a factor of 10 raised to the power of 120. That is a 1 followed by 120 zeros. This discrepancy is the cosmological constant problem, and it represents the single worst quantitative prediction in the history of theoretical physics. The theoretical value is not a little wrong. It is catastrophically, incomprehensibly, almost deliberately wrong. Physicists have been trying to understand this for decades, and no one has a satisfying answer. Some argue there must be an unknown mechanism that cancels out almost all the vacuum energy, leaving only the tiny residue we observe. Such a cancellation would require precision to 120 decimal places, with no known physical principle to explain it. Dark energy may also not be constant. Most models treat it as a fixed property of space. but measurements of cosmic expansion at different epochs hint at slight variations in the dark energy density over time. If real, these variations would mean dark energy is a dynamic field, something that evolves. Physicists call this quintessence. A strengthening dark energy field could eventually drive expansion so extreme that it tears apart all gravitationally bound structures, from galaxy clusters to galaxies, down to individual atoms and atomic nuclei. This scenario is called the Big Rip. A weakening or unstable dark energy could reverse, switching from pushing space apart to pulling it together and triggering gravitational collapse across the entire universe. We cannot predict which scenario is correct, because we do not understand what dark energy is or what governs its behavior. There is also an unsettling timing problem. Dark energy has apparently always been present, but for most of cosmic history, it was dominated by matter and played a minor role. During that matter-dominated era, gravity could pull matter together to form galaxies, stars, planets, and eventually life. That era is ending. Dark energy is becoming dominant, and as it does, it will increasingly prevent the formation of new structures. Galaxies are already accelerating away from each other. In the far future, they will recede beyond our observable horizon, and star formation will cease, existing stars will burn out, and black holes will slowly evaporate over unimaginable timescales. We happen to exist during a narrow window in cosmic history when structure formation is possible. Before this window, the universe was too hot and dense for complex chemistry. After it, the universe will be too diffuse and cold. Why are we here precisely during this brief interval? Is it simply coincidence, or is there some anthropic principle at work? The question has no clean answer, and the discomfort it creates is real. Dark energy is also erasing the cosmic record. As galaxies accelerate beyond our observable horizon, the information they carry becomes permanently inaccessible. There are galaxies we can currently observe whose future light will never reach us because they are receding faster than light propagates through expanding space. In 1 trillion years, any civilization that exists will look outward and see almost nothing. Their observable universe will contain only their local gravitational neighborhood. They will have no cosmic microwave background to analyze, no distant galaxies to measure expansion against. They will have no way to discover that a Big Bang occurred. The evidence of cosmic history will have been erased by the very expansion it set in motion. This raises an uncomfortable question. How much has already been erased? What physical phenomena occurred in the first moments after the Big Bang that left no lasting trace? If the universe destroys its own history, how incomplete is the record we are reading? When cosmologists simulate the formation of large-scale structure, starting from the smooth early universe and allowing gravity to pull matter together over billions of years, they produce a specific pattern. Matter accumulates along vast filaments and sheets, forming a cosmic web of interconnected structure with enormous voids in between. When astronomers map the actual universe, they do see this cosmic web. The overall pattern matches simulations well. The scale does not. Simulations predict that the filaments and voids of the cosmic web should have a characteristic size of roughly 300 million light-years based on the density fluctuations seeded in the early universe and the amount of time gravity has had to work. Observations consistently find filaments and voids far larger. We are finding voids exceeding 1 billion light-years across. We are finding filaments stretching billions of light-years. Gravity has not had enough time to build structures this large, even with dark matter assisting. This is not a problem isolated to one exceptional structure, like the Hercules Corona Borealis Great Wall. The entire web appears to be scaled up beyond prediction. Either the initial density fluctuations of the early universe were dramatically larger than our models assume, or structure formation proceeded through mechanisms faster and more efficient than we understand, or something is organizing matter on these scales that is not in any current theory. The problem extends to our own solar neighborhood. Several outer planets, particularly Uranus and Neptune, show tiny but persistent orbital anomalies that have puzzled astronomers for decades. In the 1980s, scientists tracking the Pioneer 10 and 11 spacecraft, launched in the early 1970s to explore the outer solar system, noticed something unexpected. The spacecraft were decelerating very slightly, experiencing a tiny, consistent acceleration directed toward the Sun that could not be explained by gravity, solar radiation pressure, or any known force. This anomaly was so small, approximately 8.7 times 10 to the negative 10 meters per second squared, that it took years to confirm it was not measurement error. Eventually, careful thermal modeling showed that anisotropic heat radiation from the plutonium power sources was creating a tiny rocket effect as it escaped preferentially in certain directions. A mundane explanation. But the outer solar system continues to offer puzzles. The Kuiper Belt, the region of icy bodies beyond Neptune, ends abruptly at approximately 50 astronomical units from the Sun in what astronomers call the Kuiper Cliff. Beyond that edge, almost nothing exists until the scattered disk and Oort cloud at far greater distances. In a solar system formed from a smooth disk of material, the Kuiper Belt should fade gradually rather than cutting off sharply. The leading hypothesis is that an undiscovered planet, designated Planet 9, orbits at extreme distance in the outer solar system and its gravity has cleared the region beyond the cliff. Multiple distant Kuiper Belt objects have orbits that cluster in unusual ways, statistically consistent with gravitational shepherding by an unseen massive object. But despite extensive searches, no one has found Planet 9. Either we are missing an entire planet in our own solar system, or the clustered orbits in the Kuiper Cliff result from some dynamical process we have not yet identified. Either option represents a gap in understanding of the place we live. Among the most powerful phenomena the universe produces are fast radio bursts. In 2007, astronomers examining archival data from the Parkes telescope in Australia found a brilliant millisecond pulse of radio waves. It lasted mere milliseconds, but released as much energy as the Sun emits in an entire day. It came from a distant galaxy billions of light years away. Initially dismissed as a fluke, repeated analysis found more events, and more after that. We now know that fast radio bursts are extraordinarily common, with thousands occurring somewhere across the full sky every single day. Most are one-time events, a single brilliant flash from a distant source that never repeats. Some repeat on irregular schedules. The energy requirements for these events are staggering. To release that much radio emission in milliseconds requires extreme astrophysics. The leading candidates are magnetars, neutron stars, with magnetic fields thousands of times stronger than ordinary neutron stars. Sudden changes in their magnetospheres, starquakes, or magnetic reconnection events could produce bursts matching the observed properties. But no single model explains all the observations. Repeating fast radio bursts behave differently from non-repeating ones. Some come from active star-forming galaxies, others from quiet, ancient elliptical galaxies. The diversity suggests either multiple mechanisms or physics more complex than current models contain. There is another possibility that physicists acknowledge carefully, without committing to it. Some fast radio bursts could be artificial. A civilization with sufficient technology could produce focused radio beams at energies matching what we observe, either for communications across intergalactic distances or for propelling spacecraft using directed energy. Clarke's third law states that any sufficiently advanced technology is indistinguishable from magic. We might add a corollary. Any sufficiently advanced technology could be indistinguishable from astrophysics. The Breakthrough Listen project monitors for patterns or modulations in fast radio bursts that might indicate artificial encoding. Nothing conclusive has been found. But the fact that we cannot definitively exclude this interpretation is itself informative about how little we understand these events. The silence of the galaxy is its own mystery. Enrico Fermi famously posed the question during a casual lunchtime conversation in 1950. If the galaxy is billions of years old and contains hundreds of billions of stars, why do we see no evidence of other technological civilizations? Even if intelligent life is extraordinarily rare, some civilizations should be far older than ours. Older civilizations should have had time to expand through the galaxy, or at least to make their presence detectable, and yet we see nothing. No signals, no megastructures, no artifacts. The silence is total. Every proposed solution to this paradox carries its own problems. If civilizations routinely destroy themselves through war, environmental catastrophe, or technological accident, why do we find no ruins? If interstellar travel is effectively impossible, physics does not obviously forbid it, merely makes it slow and expensive. If civilizations choose to remain silent and undetectable, why would every civilization independently reach the same decision? One of the darker solutions is game theoretic. In a universe where you cannot assess another civilization's intentions in advance, revealing your existence creates risk. A civilization that knows about you and is more advanced could choose to eliminate you as a potential future threat. The safest strategy is silence. And if you detect another civilization, destroying it preemptively before it can threaten you becomes a rational calculation. This scenario, sometimes called the dark forest hypothesis, would produce exactly what we observe: total silence, with every civilization hiding, listening, and broadcasting nothing. Earth has been transmitting radio signals for over a century. Any civilization within roughly 100 light-years has potentially already detected us. We made this choice before we understood its possible implications. The Great Filter Hypothesis offers a more structural explanation. Perhaps there exists some developmental step in the path, from chemistry to galaxy-spanning civilization so extraordinarily difficult that almost no lineage of life makes it through. If this filter lies behind us, perhaps in the origin of life itself, or in the emergence of complex multicellular organisms, then we are rare survivors, and most of the universe is lifeless. If the filter lies ahead, then every civilization reaches a certain level of technology and is then destroyed by something, perhaps self-inflicted, perhaps something in the environment, perhaps a physics experiment that goes catastrophically wrong. In that case, we are approaching a barrier that has ended every species before us. We have no way to determine which scenario is correct. We have a sample size of 1, but the implications of each possibility are so different that the uncertainty itself is unsettling. At the foundation of modern physics lie two frameworks of extraordinary power and extraordinary incompatibility. Quantum mechanics describes the behavior of particles at subatomic scales with breathtaking precision. General relativity describes the behavior of gravity and spacetime at cosmic scales with equal precision. Both have been tested exhaustively. Both have passed every experimental test ever devised. And when you try to combine them into a single mathematical framework, the equations produce infinities. The math literally breaks down. General relativity treats spacetime as a smooth, continuous fabric. Quantum mechanics says everything is discrete and probabilistic. The incompatibility is not a technical wrinkle awaiting a clever calculation. It is a deep conceptual contradiction suggesting that one or both frameworks is missing something fundamental. String theory attempts to resolve the incompatibility by replacing point particles with tiny one-dimensional vibrating strings. In this framework, gravity emerges naturally as one of the vibrational modes, and the mathematics is finite, avoiding the infinities of other approaches. But string theory requires extra dimensions beyond the familiar 4 of spacetime, typically 10 or 11 total. These extra dimensions must be curled up at scales far too small to detect. And there are an astronomical number of ways to perform this compactification, each producing a different set of physical laws. The landscape of string theory may contain 10 raised to the power of 500 possible configurations, each corresponding to a different universe with different constants and different physics. This means string theory may not predict our universe at all. It may predict every possible universe, which is equivalent to predicting none in particular. Loop quantum gravity takes a different approach, keeping spacetime four-dimensional but making it discrete at the smallest scales, granular rather than continuous. This eliminates infinities in a different way, but has difficulty reproducing general relativity at large scales and does not naturally include the other fundamental forces. We have two mathematically beautiful, empirically successful theories that cannot be reconciled, and no complete proposal for how to reconcile them. This is not just an academic gap. It means we cannot describe what happens inside black holes, where gravity is strong and quantum effects matter simultaneously. It means we cannot model the first moments of the Big Bang. We are blocked from understanding the most extreme physical conditions in the universe precisely because our two best tools do not work together. This incompatibility generates a specific and profound puzzle involving black holes. When matter falls into a black hole, what happens to the information it carries? Every physical system has an information content, a complete description of the state of its particles, fields, and configurations. General relativity says this information falls into the singularity and is lost from the universe forever. Quantum mechanics says information cannot be destroyed. It can be scrambled and redistributed, but the total information content of any closed system must remain constant. In the 1970s, Stephen Hawking demonstrated that black holes are not entirely black. Quantum effects near the event horizon cause the spontaneous creation of particle pairs. One particle falls inward while the other escapes, carrying away energy. Over astronomical timescales, a black hole loses mass through this process and eventually evaporates completely. But the radiation it emits is thermal, meaning it is random and carries no information about what originally fell in. When the black hole is gone, where did the information go? Physicists have been arguing about this for 50 years. The debate has produced a striking idea: the holographic principle. This proposes that all the information about a volume of space can be encoded on the two-dimensional surface surrounding it. For a black hole, everything that falls in is somehow encoded on the event horizon. When the hole evaporates, that information is released in subtle correlations within the radiation. The mathematics supporting this idea comes from a framework called the AD-CFT correspondence, which relates quantum gravity in certain spacetimes to simpler quantum theories on their boundaries. If the holographic principle is correct, it has implications far beyond black holes. It might mean that the entire universe is holographic, that the three-dimensional depth we experience is a projection of information stored on a distant two-dimensional boundary. A holographic universe and a simulated universe are, in terms of their information structure, mathematically equivalent. Whether the substrate encoding our reality is called a hologram or a simulation is a matter of language rather than physics. At the foundations of quantum mechanics itself lies an unresolved problem that touches everything else. Quantum systems exist in superpositions, multiple states simultaneously, until they are measured or interact with a measuring apparatus. When measurement occurs, the superposition collapses into a single definite outcome. But quantum mechanics does not explain what constitutes a measurement, what triggers collapse, or why any particular outcome rather than another occurs. This is the measurement problem, and it has been unresolved since the theory's founding in the 1920s. The Copenhagen interpretation, the default textbook account, simply asserts that measurement causes collapse without explaining the mechanism. It treats measurement as a fundamental process outside the equations. The many worlds interpretation takes the opposite stance, proposing that superpositions never collapse. Every possible outcome of every quantum measurement occurs simultaneously in different branches of a universal wave function. You experience one outcome, but other versions of you in other branches experience all the other possibilities. All branches are equally real, just mutually inaccessible. This interpretation is mathematically clean but requires multiplying the number of real universes by an essentially infinite factor to account for every quantum event in every system across all of cosmic history. Other interpretations, including pilot wave theory and objective collapse theories, each resolve the measurement problem in different ways, each with their own experimental predictions and theoretical costs. All of them make identical predictions for every practical experiment we can currently perform. We cannot distinguish between them. Quantum mechanics tells us exactly what will happen with extraordinary precision, but we do not know what it means, and the different possible meanings have drastically different implications for the nature of reality. These interpretational questions are not purely philosophical. They affect how we think about cosmology and the entire history of the universe. If many worlds is correct, the Big Bang did not produce one universe. It produced an infinite tree of universes containing every possible quantum history. If objective collapse is correct, the early universe may have behaved differently from microscopic quantum systems, affecting how structures formed. The measurement problem sits beneath everything and remains unsolved. Among the quantitative anomalies in cosmology, one of the most persistent is the lithium problem. In the first few minutes after the Big Bang, in a process called Big Bang nucleosynthesis, conditions were hot and dense enough for nuclear reactions to produce the first light elements. Calculations based on the density and temperature of the early universe precisely predict how much hydrogen, helium, and lithium should have been produced. For hydrogen and helium, the predictions match observations beautifully. The universe is approximately 75% hydrogen and 25% helium by mass, exactly as calculated. But lithium-7, the most abundant isotope of lithium, appears at roughly 1/3 the predicted abundance in the oldest stars we can observe. These are metal-poor stars from the first stellar generations, which should have preserved primordial abundances with minimal modification, but they consistently fall short of the predicted lithium level by a factor of 3. All proposed solutions create new problems. Adjusting stellar models to allow more lithium destruction during stellar evolution requires conditions that are not clearly universal across all old stars. Adjusting the nuclear reaction rates used in nucleosynthesis calculations to reduce lithium production breaks the agreement for hydrogen and helium. Invoking new physics, additional particle species or dark matter interactions that reduced lithium production in the early universe, requires extending the standard model without experimental evidence. The lithium problem remains unresolved, a quiet but stubborn discrepancy embedded in the most successful calculation in cosmological history. Among the most energetic phenomena in physics are ultra-high-energy cosmic rays. These are particles, mostly protons, that arrive at Earth from space with energies exceeding 10 raised to the power of 20 electron volts. That is macroscopic energy concentrated in a single subatomic particle comparable to the kinetic energy of a thrown baseball. We have no idea how nature accelerates particles to this extreme. Supernova shockwaves, the conventional accelerators for ordinary cosmic rays, fall orders of magnitude short. Proposed mechanisms include the intense magnetic and gravitational fields near supermassive black holes and the extreme conditions in colliding galaxies. But a fundamental constraint makes the problem worse. Protons at this energy interact with the photons of the cosmic microwave background through a process that produces pions, and this interaction drains their energy rapidly. Above a certain energy threshold, a proton can only travel about 50 million light-years before falling below detection threshold. This means the most energetic cosmic rays must come from relatively nearby sources. But when astronomers trace their arrival directions back through galactic magnetic fields, they do not point to obvious nearby sources. Some appear to originate from voids, empty regions containing no known galaxies or energy sources. Either our understanding of how these particles propagate through the galaxy is wrong, or the sources are exotic in ways we have not identified, or there are acceleration mechanisms in the large-scale structure of the universe that no current theory describes. There is also mounting evidence that the universe may not be as rotationally symmetric as the cosmological principle requires. Analysis of the polarization angles of distant quasars, which reflect the orientation of magnetic fields along their lines of sight, shows coherent alignment across scales of billions of light-years. Independent regions of the universe should have randomly oriented magnetic fields. This alignment should not exist. Galaxy rotation axes within the filaments of the cosmic web also show alignment that extends beyond what local gravitational torquing would produce. If both effects are real, and not artifacts of observational selection or systematic measurement error, they imply that the universe has large-scale preferred directions embedded in its magnetic and rotational structure. This would require something in the early universe, perhaps primordial magnetic fields, perhaps topology, perhaps pre-inflationary physics, to have seeded these coherent orientations across distances we can barely measure. One area where the standard model faces a quantitative rather than structural crisis is the Hubble tension. The Hubble constant is the rate at which the universe expands, measuring how fast distant galaxies recede per unit of distance. There are two independent methods of measuring it, and they consistently disagree. The first method uses the cosmic microwave background and the standard cosmological model to infer the expansion rate. This approach, most precisely performed by the Planck satellite, gives a Hubble constant of approximately 67 kilometers per second per megaparsec. The second method builds a cosmic distance ladder using variable stars called Cepheids to calibrate Type Ia supernovae as distance markers and then measures recession velocities directly. This approach, led by teams including the SHAISH 0ES collaboration with Adam Rees, consistently yields a Hubble constant of approximately 73 kilometers per second per megaparsec. The discrepancy is about 9%. That sounds small. In physics at this level of precision, with both methods refined over decades, it is enormous. The two values disagree at a statistical significance of roughly 5 sigma, meaning the probability that random measurement error accounts for the difference is about 1 in a million. The most boring explanation is systematic error in one or both measurement chains. Astronomers have checked relentlessly. The discrepancy persists through independent calibrations and multiple independent teams. If the disagreement is real, it implies either the standard cosmological model is wrong and our universe's early history differs from what we assume, or the physics between the early and late universe changed in ways we have not modeled. Some researchers have proposed early dark energy, an additional energy component that was significant in the early universe and then faded, which would alter the acoustic scale in the cosmic microwave background and shift the inferred Hubble constant upward. Others suggest that dark energy is not constant, but evolves over time. None of these modifications yet fully resolves the tension without introducing new problems elsewhere. The Hubble tension has become one of the most closely watched unsolved problems in all of observational cosmology. General relativity describes what happens when mass and energy curve spacetime, and the theory's predictions have been confirmed to extraordinary precision across solar system scales and in binary pulsar systems. But at the extreme conditions inside black holes, the theory breaks down. It predicts singularities, points of infinite density and infinite spacetime curvature, where the equations cease to be meaningful. In black holes, we observe, singularities are hidden behind event horizons, surfaces from which nothing can escape. This arrangement, called the cosmic censorship hypothesis, was proposed by Roger Penrose. It states that singularities are always concealed and can never be observed directly. But the cosmic censorship hypothesis is a conjecture. It has not been mathematically proven for all possible physical scenarios. Some exact solutions to Einstein's field equations permit naked singularities, singularities without event horizons, from which light and information can escape. If naked singularities exist in nature, they would represent observable points where general relativity fails completely, regions where any prediction is possible and none are reliable. Whether this would be scientifically useful or physically catastrophic, possibly both, depends on what physics actually governs behavior at the singularity, which we cannot currently say because we lack a theory of quantum gravity. Most numerical simulations of gravitational collapse suggest that event horizons always form before singularities become visible, preserving censorship in practice, but the mathematical proof remains elusive. General relativity also permits a theoretically alarming class of spacetime geometries called closed time-like curves. These are paths through spacetime that loop back to their own starting point in time. A particle following such a path would return to its own past. Kurt Gödel, the mathematician famous for incompleteness theorems, discovered in 1949 that Einstein's field equations admit a solution describing a rotating universe filled with closed time-like curves everywhere. In this space-time, you could travel into your own past simply by journeying far enough in the right direction. Einstein found the implication deeply disturbing. Most physicists believe closed time-like curves cannot exist physically. Quantum mechanical effects appear to prevent their formation through what is called chronological protection. Quantum fluctuations would become infinitely intense and destroy any mechanism attempting to create a time loop before it could function. But this argument rests on semi-classical calculations that approximate quantum gravity rather than using a complete quantum theory of gravity. Until quantum gravity is understood, we cannot say definitively whether nature permits or forbids paths through time. The arrow of time is perhaps the deepest mystery of all. We remember the past, not the future. Entropy increases. Eggs shatter and do not reassemble. Perfume diffuses through a room and does not spontaneously recollect into the bottle. These facts are so obvious that they seem to need no explanation. But the fundamental laws of physics are time-symmetric. Particle collisions played backward in time still satisfy every known physical law. There is no equation of fundamental physics that prefers one time direction over the other. The second law of thermodynamics tells us that entropy, the measure of disorder in a system, tends to increase over time, and this gives time a macroscopic arrow. The future is the direction in which entropy is higher. But this only moves the question: why does entropy increase? The statistical answer is that high entropy, disordered states, are astronomically more probable than low entropy, ordered states. A system evolves toward higher entropy because there are vastly more disordered configurations available. But this just pushes the mystery back one step further. Why did the universe begin in an extraordinarily low entropy state? The Big Bang was an incredibly ordered configuration, all matter and energy concentrated in a tiny volume with specific, tightly constrained initial conditions. If the universe began in thermal equilibrium at maximum entropy, nothing would happen. Time would be directionless. We have an arrow of time because the universe was born far from equilibrium, and everything since has been the slow progression toward equilibrium. We do not know why those initial conditions existed. They are assumed in every cosmological model, not derived from any deeper principle. The arrow of time, the most fundamental feature of our experience, is an unexplained initial condition. This catalog of anomalies touches nearly every scale and every domain of physics. The universe is expanding faster and faster, driven by an energy that is quantitatively wrong by 120 orders of magnitude compared to the only available theoretical prediction. It is filled with matter we know exists and have mapped, but cannot identify or directly detect. It contains structures too large and too massive to have assembled in the available time. Its oldest visible objects may be older than the universe itself. Its largest scale temperature map is not statistically uniform. Something outside our observable horizon is pulling clusters of galaxies through the expanding fabric of space. The black holes formed in the early universe grew far too quickly for any known mechanism. The mathematical frameworks that describe the smallest and largest scales of nature cannot be reconciled. The two most reliable measurements of the universe's expansion rate disagree by 9%, and the disagreement is statistically not a coincidence. And the most fundamental fact of our experience, that time flows forward, remains without a physical explanation. Does this mean physics is broken? No, it means physics is incomplete. Every anomaly we have discussed represents not a failure but an opening, a place where new understanding can enter. The history of science is a history of exactly this pattern. Newtonian mechanics described the motion of planets with extraordinary accuracy until Mercury's orbit precessed slightly too fast. Einstein's general relativity emerged to fix it. Classical physics explained thermodynamics and electromagnetism until the spectrum of radiation from a heated body contradicted every prediction. Quantum mechanics emerged to fix it. The standard model of particle physics explained the behavior of every known particle until neutrinos were observed changing from one type to another in flight. Physicists extended the model to include neutrino mass. Each time a clean anomaly was identified and taken seriously, a deeper theory emerged. The anomalies we face now are harder and more numerous. They resist resolution into any simple extension of existing frameworks. Some physicists believe what is required is not an extension, but a replacement, a conceptual revolution as fundamental as quantum mechanics was to classical physics or relativity was to Newtonian gravity. Others believe the pieces are nearly in place, and the missing element is one or two key experimental results, or one theoretical insight that reorganizes what we already know. The next breakthrough could come from any direction. A particle detector that finally catches a dark matter interaction after decades of searching. Gravitational wave observations of neutron star mergers or exotic compact objects that test general relativity in regimes no other instrument can access. Astronomical surveys that map the cosmic web and galaxy rotation across larger volumes with greater precision, sharpening every tension we have described. Quantum computers that enable calculations in quantum gravity currently impossible for any classical system. Or a theoretical insight that reorganizes the relationship between information, space-time, and quantum mechanics into something that resolves the black hole information paradox, the Hubble tension, and the cosmological constant problem simultaneously. We do not know which direction the resolution will come from. We know only that the universe is telling us, with increasing clarity and in multiple independent observations, that something fundamental is missing. We are living in a specific and perhaps privileged moment in scientific history. We have built instruments capable of seeing the edge of the observable universe, detecting space-time ripples from black hole collisions, and measuring temperatures and distances to precisions that would have seemed impossible 50 years ago. And the more precisely we measure, the more clearly the contradictions come into focus. We are not discovering that the universe is simpler than we thought. We are discovering that it is stranger. The question before the current generation of physicists and astronomers is whether the strangeness is a symptom of instruments revealing the limits of our theories, or whether it is pointing directly at a deeper reality waiting to be understood. There are two possible emotional responses to this state of knowledge. One is unease, the sense that the ground beneath our understanding is less solid than we believed. The other is curiosity, the recognition that we are living at the edge of human knowledge, where the next genuine discovery about the fundamental nature of reality might be made at any moment. Both responses are reasonable. What would be unreasonable is indifference. We have mapped the cosmic microwave background from one end of the observable universe to the other and found a cold spot no theory predicts. We have measured the expansion rate of the universe with two independent methods and found results that disagree at the level of statistical certainty. We have pointed our most powerful telescope at the early universe and found galaxies and black holes that should not exist in the time available. We have searched underground for dark matter particles for decades and found nothing. We have watched galaxies drift towards something beyond our horizon that we will never see. These are not minor rounding errors. They are the universe insisting that we revise our understanding of it. The civilizations that came before us looked at the same night sky and saw mystery. Most interpreted that mystery as the domain of the divine and accepted that human understanding had a ceiling. We are the first civilization that has refused to accept that ceiling, that built instruments of extraordinary precision and has taken the resulting contradictions seriously rather than explaining them away. Every anomaly we have discussed in this account exists because some scientist insisted on measuring something carefully, reporting a result that did not fit existing theory, and refusing to accept dismissal. The cold spot exists in our cosmological maps because the Wilkinson Microwave Anisotropy Probe team reported it and the Planck team confirmed it, even knowing it would be controversial. The dark flow exists in our velocity catalogs because Alexander Kashlinsky's team measured it and stood by the result. The Hubble tension exists because both measurement teams trusted their data over theoretical convenience. This is how knowledge advances, not by assuming theories are correct, but by measuring reality carefully and reporting honestly what the measurements show. The universe does not owe us a simple, comprehensible structure. It has no obligation to match our theoretical expectations. The fact that it can be measured at all, that mathematics invented in the minds of humans describes the behavior of matter and energy across cosmic distances with extraordinary precision, is itself remarkable and unexplained. Why should the universe be mathematical? Why should its laws be discoverable by beings who evolved to find food and avoid predators on one small planet? We do not know, but they are, and we can, and we are. The anomalies accumulating in cosmology and physics are not a sign of failure. They are a sign of success. We have measured enough to know what does not fit. We have refined our theories enough to see where they crack. A century ago, we did not know dark matter existed. We had no concept of dark energy. We had not discovered the cosmic microwave background. We had no idea what caused galaxy rotation curves, or that the expansion of the universe was accelerating, or that supermassive black holes formed at the universe's center. Everything we now identify as an anomaly was first discovered as nothing at all, invisible, unmeasured, unknown. The fact that we now know enough to be confused is genuine progress. The work ahead is to build better detectors, survey larger volumes of sky, refine the cosmic distance ladder, search for dark matter with instruments of even greater sensitivity, push gravitational wave detectors to listen for signals from earlier and more exotic events, and develop the theoretical frameworks that might finally unify quantum mechanics with gravity and illuminate what dark energy actually is. Somewhere in the intersection of better measurements and deeper theory, the next great revolution in physics is waiting. It may arrive as a single anomalous data point that refuses every conventional explanation. It may arrive as a theoretical calculation that suddenly makes multiple separate mysteries coherent. It may arrive in a way that no one currently anticipates. What is certain is that the universe has not finished surprising us. The cold spot in the cosmic background, the axis of evil, the dark flow, the structures too large to exist, the stars too old to have formed, the black holes that grew too fast, the dark matter we cannot catch, the dark energy we cannot explain, the Hubble tension that will not resolve, the arrow of time with no physical origin. All of these are the universe speaking in the only language it knows how to use: measurement, data, contradiction with expectation. Every one of these anomalies is an invitation to measure more carefully, to think more deeply, to revise our assumptions more honestly. We look up at the night sky and see points of light. Behind those points of light is ancient radiation, carrying the thermal imprint of a universe 380,000 years old. Behind that radiation is a geometry we cannot fully map, filled with matter we cannot see, permeated by energy we cannot explain, organized at scales that should be impossible, evolving in a direction our equations cannot predict, and containing at its foundation two incompatible mathematical frameworks that each describe their domain with astonishing accuracy. All of this is real. All of it is there. All of it is waiting. If you find yourself compelled by these questions, by the genuine open problems in our understanding of reality, the best thing you can do is stay curious. Support the science that pushes into these dark territories. And when you hear that physicists have found yet another anomaly, yet another measurement that does not fit, do not interpret it as a sign that science has failed. Interpret it as a sign that science is working. The anomalies are how the next revolution announces itself. Nothing makes sense anymore because we have finally learned enough to realize how much we do not yet understand. That is not a conclusion, that is a beginning. We have not yet discussed one of the most precisely measured and most troubling discrepancies in all of modern physics, the anomalous magnetic moment of the muon. The muon is an elementary particle identical to the electron in every way except that it is roughly 207 times heavier and inherently unstable, decaying in microseconds into lighter particles. Like all charged particles, it has a magnetic moment, a quantity describing how strongly it interacts with magnetic fields. Quantum electrodynamics, the quantum theory of electromagnetism, can predict the muon's magnetic moment to extraordinary precision. It is one of the most precisely calculated quantities in all of theoretical physics. For decades, the predicted value matched experimental measurements to more than 10 significant figures, an astonishing confirmation of the theory. Then experiments at Brookhaven National Laboratory in the early 2000s, and later, more precisely at Fermilab, starting in 2018, measured the muon's magnetic moment with even greater precision. The measured value is slightly larger than the theoretical prediction. The discrepancy is small in absolute terms, but at statistical significance exceeding 4 sigma, it is not the kind of gap that disappears with better instruments. Current Fermilab data pushes the significance toward 5 sigma, the conventional threshold for declaring a discovery. If the discrepancy is real and not an artifact of the theoretical calculation, it means the muon is interacting with something that the standard model does not account for. Some undiscovered particle or field is contributing to its magnetic moment. This would be the first clear experimental evidence of physics genuinely beyond the standard model. Some theoretical physicists have proposed explanations involving supersymmetric particles, new gauge bosons, or dark sector interactions. None of these proposals is confirmed. There is also ongoing controversy about the theoretical calculation itself. A detailed calculation using lattice quantum chromodynamics, a numerical technique for computing strong force contributions, yields a result that, if correct, would reduce the discrepancy with experiment. The theoretical community is divided on which calculation is more reliable. The resolution of this disagreement is one of the most active fronts in theoretical particle physics. But if the experimental result stands, and the standard calculation is correct, we have measured evidence of something new interacting with ordinary matter. Something the most successful theory in the history of physics does not describe. The standard model itself has a deep, unexplained structure. It describes 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. It contains 17 fundamental particles organized into patterns that theoretical physicists find strongly suggestive of deeper mathematical structure. The forces unify at high energies in ways that make physicists suspect all 3 gauge interactions might be aspects of a single underlying symmetry, a grand unified theory. But no grand unified theory has been confirmed experimentally. The simplest versions predict that protons should be unstable, slowly decaying into lighter particles over a timescale of around 10 raised to the 31 to 32 years. Experiments monitoring large volumes of water in underground detectors, shielded from cosmic rays, have watched for proton decay for decades without observing a single event. This rules out the simplest grand unified theories, but does not rule out unification entirely. More complex theories predict longer proton lifetimes that experiments cannot yet reach. The Standard Model also fails to accommodate gravity. It describes the other three forces through quantum field theories, each with associated carrier particles, but attempts to include gravity by analogy, inventing a graviton as the carrier of the gravitational force, consistently produce theories full of uncontrollable infinities. This is not a technical problem awaiting a clever mathematical trick. It reflects a genuine incompatibility between the principles of quantum mechanics and the principles of general relativity. Physicists have known this for nearly a century and have not resolved it. There is also the matter of the universe's matter-antimatter asymmetry. The Big Bang should have produced equal quantities of matter and antimatter. When matter and antimatter meet, they annihilate each other, converting entirely into energy. If the early universe contained equal amounts, everything should have annihilated, leaving only radiation. We would not exist. The fact that we are here, composed of matter, means the early universe had a slight excess of matter over antimatter, roughly 1 part in a billion. After all the annihilation, that small excess of matter became everything that exists. Every galaxy, every star, every planet, every atom in your body. The asymmetry is required by our existence, but is not explained by any aspect of current theory. The Standard Model allows for a small amount of asymmetry through a phenomenon called charge parity violation, which causes matter and antimatter to behave slightly differently in certain weak force interactions. But the asymmetry the Standard Model allows is far too small to account for the 1 in a billion excess we require. Something else in the physics of the early universe generated the material asymmetry we observe. We do not know what. These questions converge at the moment of the Big Bang itself. Our best description of the very early universe, in the first fraction of a second, relies on extrapolating the known laws of physics to conditions of temperature and density so extreme that those laws have never been tested there. The Planck epoch, the first 10 raised to the negative 43 seconds after the Big Bang, is the domain where quantum gravitational effects should dominate. Before a theory of quantum gravity exists, we literally cannot say anything about what happened during that interval. We cannot describe the initial conditions of the universe. We cannot explain why the universe had low entropy at its beginning, or why it had the matter-antimatter asymmetry it had, or why the fundamental constants have the values they have, or why space has 3 large dimensions rather than some other number. All of these features are inputs to our models, not outputs. They are assumed, not derived. Our entire understanding of cosmic history begins after the first quantum gravitational instant, and we cannot see behind that wall. Some cosmological frameworks propose that the observable universe emerged from a quantum fluctuation in a pre-existing quantum vacuum, or from a cyclic process in which universes collapse and bounce, or from an inflationary expansion in a larger multiverse within which other universes are constantly nucleating. These are legitimate scientific proposals with mathematical frameworks behind them. They are not confirmed. Some make predictions that are in principle testable, such as specific patterns in the primordial gravitational wave background, or specific non-Gaussian features in the cosmic microwave background. Future gravitational wave detectors, like the Laser Interferometer Space Antenna, planned to fly in the 1930s, may begin to probe these predictions. But for now, what came before the Big Bang, or whether the question is even meaningful, is entirely beyond our reach. The universe we can observe has a horizon. Light can only have traveled a finite distance in the finite time since the Big Bang, meaning there is a maximum distance beyond which we receive no information. This observable horizon is a sphere roughly 46 billion light-years in radius. Everything beyond it is causally disconnected from us, not temporarily, but fundamentally. Light from those regions has not had time to reach us, and may never reach us, particularly given that dark energy is accelerating the expansion and more regions are crossing beyond our horizon over time. There may be more universe beyond our horizon, perhaps an infinite amount, and we will never observe it. Some models suggest the conditions beyond the horizon are similar to conditions here. Others suggest they vary widely, with different values of fundamental constants and different physical structures. This is untestable by definition, and yet the question of whether our observable patch is typical or unusual within a larger reality has profound implications for interpreting everything we observe. The fine-tuning problem goes beyond any single constant. It extends to the overall structure of the laws of physics. Why does the universe have the specific particle content and force structure of the Standard Model? Why 3 generations of quarks and leptons? Why the specific pattern of symmetries? Why do the mathematical relationships between the constants permit the formation of stable atoms, nuclear chemistry, stellar fusion, and the energy flows that sustain living systems? Theoretical physicists have found that relatively small changes to the fundamental constants would make the universe sterile. A slightly stronger electromagnetic force and nuclei would not hold together. A slightly weaker strong force and protons would not bind. A cosmological constant only slightly larger, and the universe would have expanded too quickly for any structure to form. We exist in a universe that is, by any reasonable measure, extraordinarily hospitable to complexity. Is that a coincidence, a selection effect, or evidence of something we have not yet understood? The multiverse hypothesis offers one answer. If many universes exist, each with different values of the constants, then observers can only arise in universes where the constants permit their existence. We inevitably observe a fine-tuned universe not because there is a principle that requires it, but because we could not exist to observe an untuned one. This reasoning has a formal name, anthropic selection, and it is logically valid. It is also deeply unsatisfying to many physicists because it replaces explanation with selection. We want to know why the constants have their values, not merely why they could not have different values given that we are here. Some researchers argue that a complete theory of quantum gravity will derive the constants rather than assuming them, predicting their values from deeper mathematical necessity. That would be one of the most profound achievements in the history of science. We are far from that achievement. We do not yet know whether it is possible. These open questions are not signs of science losing ground. They are signs of the frontier. Every one of these problems is a precisely formulated, empirically grounded challenge. We can measure the Hubble tension to arbitrary precision. We can search for dark matter with steadily improving detectors. We can observe more of the early universe with future space telescopes. We can probe quantum gravity through gravitational wave astronomy. We can test the stability of the Higgs vacuum through precision collider experiments. We can search for proton decay with larger and more sensitive underground detectors. We can map the large-scale structure of the universe across greater volumes. The path from mystery to understanding is not blocked. It requires better tools, sharper theory, and the willingness to revise assumptions that have been held for decades. Scientific revolutions have a characteristic shape. They begin with precision measurements that do not fit established theory. They pass through a period of attempted accommodation, where theorists modify existing frameworks to absorb the new data. When the modifications become too strained, a new framework emerges that explains both the old success and the new anomalies from a deeper perspective. We appear to be somewhere in the middle phase, accumulating anomalies faster than accommodations can absorb them. The Hubble tension, the muon anomaly, the lithium problem, the early massive galaxies and black holes, the impossibly large cosmic structures, the nature of dark matter and dark energy. These are pulling in directions that existing frameworks accommodate only with increasing difficulty. What the new framework will look like is unknown. It may be found first in theoretical physics, a mathematical structure that resolves the incompatibility of quantum mechanics and gravity, and from which the anomalies naturally follow. It may be found first in observation, an experiment that yields a result so clearly inconsistent with all existing theories that an entirely new direction becomes obvious. Either path leads to the same destination, a deeper understanding of what the universe is made of, how it began, how it works, and perhaps whether it is the only one. We do not know how long this will take. The gap between identifying an anomaly and understanding its resolution can be years, decades, or centuries. Mercury's anomalous precession was known in the mid-1800s and resolved in 1915 with general relativity. The ultraviolet catastrophe and blackbody radiation was identified in the 1890s and resolved in 1900 with the quantum hypothesis. The neutrino was hypothetically proposed in 1930 to conserve energy in radioactive decay and was not directly detected until 1956. The universe has a way of rewarding patience in physics. What is clear is that we are at a juncture where the map runs out. On the medieval maps of unknown territories, cartographers sometimes wrote words, meaning here there be unknowns. We have drawn our map of the universe with extraordinary precision up to the limits of our instruments, and beyond those limits and embedded within the map itself, there are features we cannot explain. The cold spot in the background radiation, the dark flow of galaxy clusters, the impossibly large structures, the vanishing lithium, the expanding universe that should be slowing and is not, the matter we can weigh but never touch, the energy that fills all of space and drives everything apart. These are not empty territory. They are territory we have measured carefully enough to know is full of something we do not understand. We are the first species in the history of this planet to build instruments sensitive enough to detect the cosmic microwave background, to measure the geometry of the universe, to hear the collision of black holes in gravitational waves, to observe the first stars and galaxies forming. We are the first to reach the level of understanding where the next questions are clear and the answers are not. That is exactly where you want to be if you are a civilization that wants to understand reality. The questions are precise, the instruments are improving, the theorists are working, and the universe, strange and vast and indifferent and full of phenomena that contradict everything we thought we knew, is still out there, still measurable, still, piece by piece, understandable. If you have followed this account this far, you already know that the universe is weirder than anyone's intuition naturally accommodates. You know that the darkness between galaxies is not empty, but filled with invisible matter. That the expansion of space is being driven by something we cannot measure directly. That the oldest stars push against the limits of the universe's own age. That the largest structures in the sky should not exist. That the two most successful theories in physics are incompatible at their foundations. You know that 95% of everything is unknown, and you know that this is not a problem awaiting a cleaner data set. These are deep, genuine, unresolved mysteries at the heart of our best understanding of nature. The appropriate response to this is not despair, it is engagement. Every field in science is better attended to when people outside it understand what the real questions are. The resources devoted to resolving these mysteries, the detector facilities, the space telescopes, the particle accelerators, the theoretical centers, depend on a broader understanding of why these questions matter. Nothing makes sense anymore, as the title of the source material puts it, because we have learned enough to see the outlines of what we do not know. But knowing what you do not know is the beginning of finding out. We are just getting started. Like and subscribe if you want to follow what comes next. One of the strangest features of the observable universe is how precisely flat it is. General relativity describes the universe as having a geometry that can be positively curved like the surface of a sphere, negatively curved like a saddle, or flat like a plane. These geometries have measurable consequences for how light travels across cosmic distances and for the angular scale of temperature fluctuations in the cosmic microwave background. Measurements from the Planck satellite indicate that the universe is flat to extraordinary precision within roughly 0.5% of perfect flatness. This is astonishing. The flatness of the universe is an unstable condition in the sense that small departures from flatness in the early universe would have been amplified rapidly by the subsequent expansion. For the universe to be flat today, it must have been flat to 1 part in 10 raised to the 60th power in the first second of its existence. This is the flatness problem, and it has no natural explanation in standard cosmology without invoking inflation. Inflation, the rapid exponential expansion of space in the first tiny fraction of a second after the Big Bang, would have stretched away any initial curvature and driven the geometry toward flatness regardless of its initial value. The flatness we observe today is one of the key pieces of evidence that inflation, or something functionally equivalent to it, actually occurred. But inflation raises its own problems. Specifically, it requires a new field not present in the standard model, called the inflaton, with a potential energy that is carefully shaped to produce the right amount of expansion before inflation ends. Different proposed shapes of this potential give different predictions for the primordial gravitational wave background and for the detailed statistics of density fluctuations in the early universe. Some of these predictions have been tested by measurements of the cosmic microwave background. Others are still being tested. The Planck data constrain inflation models tightly but do not uniquely identify which model is correct. Multiple inflation models survive the current data. The most direct confirmation of inflation would be the detection of primordial gravitational waves, ripples in spacetime produced by the rapid expansion itself. These would imprint a specific pattern, called B-mode polarization, on the cosmic microwave background. Several experiments are currently searching for this signal, including ground-based telescope arrays in Chile and at the South Pole. A confirmed detection of primordial gravitational waves would provide powerful evidence that inflation occurred and would constrain the energy scale at which it happened. The absence of a signal would rule out a broad class of inflation models and potentially point toward alternative explanations for the flatness and horizon problems. Either result would be enormously informative. The horizon problem, which inflation is also designed to solve, is another indication that something dramatic happened in the earliest moments of cosmic history. When we observe the cosmic microwave background in opposite directions of the sky, looking at regions separated by tens of billions of light years, we find that their temperatures are the same to roughly 1 part in 100,000. But those regions were causally disconnected at the time the background radiation was emitted. Light had not had time to travel between them. There is no mechanism in standard physics by which causally disconnected regions could have reached thermal equilibrium. Their identical temperatures require some mechanism that either established uniform initial conditions or allowed them to interact before we would naively expect. Inflation solves this by proposing that all of the observable universe expanded from an extraordinarily small, causally connected region in the first instant. The uniformity we see is a relic of conditions in that tiny patch before it expanded. If inflation did not occur, we need some other explanation for why opposite corners of the sky look identical, an explanation that does not yet exist in any standard framework. There is also the matter of magnetic monopoles. Grand unified theories, the theoretical frameworks attempting to unify the strong, weak, and electromagnetic forces into a single interaction at high energies, generically predict the existence of magnetic monopoles. These would be elementary particles carrying a net magnetic charge, the magnetic equivalent of an electron carrying electric charge. Every known magnet, from the iron in your refrigerator to the magnets in particle accelerators, has a north pole and a south pole. Break a magnet in half and you get 2 smaller magnets, each with both poles. No matter how finely you divide magnets, you always get dipoles. Grand unified theories say that in the very early universe, when temperatures were high enough for the unified symmetry to be intact, transitions as the universe cooled would have produced magnetic monopoles at high density, 1 per causally connected region. By now, the universe should be full of magnetic monopoles. Physicists have searched for them extensively. No confirmed magnetic monopole has ever been detected. Their predicted cosmic abundance vastly exceeds the observational upper limit. This is the magnetic monopole problem. Inflation solves it by diluting the monopole density, spreading the monopoles produced in the very early universe across a volume so much larger than the observable universe that we would expect to find essentially none within our horizon. Once again, inflation appears as the solution to multiple independent observational puzzles simultaneously. But the resolution of one puzzle by inflation does not mean we understand inflation. We do not know what the inflaton field is. We do not know whether inflation is the only possible mechanism for producing a flat, uniform, monopole-free universe, or whether alternative mechanisms might do the same job. We do not know the energy scale at which inflation occurred, though measurements of the cosmic microwave background constrain it. And we do not know how inflation ended, a process called reheating, in which the energy stored in the inflaton field was converted into the matter and radiation that populated the hot early universe. Reheating models range from simple to extremely complex, and the details have consequences for the subsequent evolution of the universe. Some reheating models can generate the matter-antimatter asymmetry needed for our existence, others cannot. The particle physics of reheating is actively studied but not constrained by current data. Beyond inflation, there is a class of cosmological proposals called bouncing cosmologies. In these frameworks, the Big Bang was not a beginning, but a transition. The universe existed before the Big Bang in a contracting phase. At some point, quantum gravitational effects or exotic matter prevented the contraction from reaching a true singularity and instead caused a bounce, transitioning to the expanding phase we observe today. This idea appears in loop quantum cosmology, in ekpyrotic models inspired by string theory, and in several other frameworks. Bouncing cosmologies have the potential to avoid the flatness, horizon, and monopole problems through a different mechanism than inflation, and to explain the specific statistical features of the density fluctuations we observe in a different way. Some of these models make predictions distinguishable from inflation models for the primordial gravitational wave signal. If future experiments measure the primordial gravitational wave background with sufficient precision, it may be possible to distinguish bouncing cosmologies from inflationary ones. This would represent a direct probe of what happened at and before the Big Bang, and whether the concept of a beginning even applies to our universe. None of this is settled. The scientific community is not close to consensus on quantum gravity, on the nature of dark matter or dark energy, on the explanation for the matter-antimatter asymmetry, or on what preceded or caused the Big Bang. What is settled is that the anomalies are real and the questions are well posed. We know what we need to measure and what kind of theoretical framework would be needed to explain it. The experimental programs are underway. The theoretical work is ongoing. The universe is not keeping its secrets because they are in principle inaccessible. It is keeping them because the instruments and theories needed to unlock them are still being built. There is a perspective from which all of this is deeply encouraging. Every question answered in the history of science was at some point completely mysterious. The nature of fire, the cause of disease, the composition of stars, the age of the universe, the structure of DNA. Each of these seemed impossibly complex before the right conceptual framework and the right experimental tools came together to illuminate it. Dark matter is not more mysterious in principle than the composition of stars was before spectroscopy existed. Dark energy is not more resistant to understanding in principle than radioactivity was before nuclear physics existed. Quantum gravity is not more inaccessible in principle than atomic structure was before quantum mechanics existed. The history of science is a history of mysteries resolved by new conceptual frameworks made possible by new experimental capabilities. We have no reason to believe the pattern will not continue. What the accumulated anomalies of modern cosmology and physics suggest is that we are approaching one of those transitions, one of those moments when the existing framework is strained by enough contradictions that a deeper one becomes necessary. These moments are rare in the history of science. They are also the most exciting. We do not know what the next framework will look like. We do not know whether it will emerge from a theoretical breakthrough, an experimental discovery, or both simultaneously. We do not know whether it will be built by someone working today or someone not yet born, but we know the anomalies are there, measured and confirmed, and they are pointing somewhere. They are pointing toward a truth about the universe that we have not yet grasped. That truth exists, and somewhere in the data we are collecting, the calculations we are performing, and the instruments we are building, the path to it is already beginning to take shape. There is one more anomaly worth discussing, and it may be the most unsettling of all, precisely because it is so intimate. The brain you are using to read or hear this account is composed of atoms whose origin we partly understand and partly do not. The hydrogen atoms in your body formed in the Big Bang itself. The heavier elements were forged in the nuclear cores of stars that lived and died before the sun existed. The gold in any jewelry you own formed in the collision of neutron stars. You are, in the most literal sense, assembled from cosmic events spanning the entire history of the universe. This is not poetry, it is astrophysics. And the atoms in your brain are organized in a configuration that allows something called consciousness, awareness, subjective experience, the feeling of being you perceiving this moment. We do not understand what consciousness is. We do not know whether it is a fundamental feature of certain information processing systems or an emergent property of neural complexity or something else entirely. We do not know whether it is in principle explainable by physics or whether it points to something genuinely outside our current frameworks. This is not a soft philosophical question tacked onto the end of a physics discussion. It is a hard scientific question with real empirical content. The study of consciousness involves neuroscience, physics, information theory, and philosophy in ways that have not yet converged on a common framework. Integrated information theory proposes that consciousness is a fundamental property of certain information processing structures and attempts to quantify it. Global workspace theory proposes that consciousness arises from a particular architecture of information broadcasting in the brain. Quantum theories of consciousness, though controversial, propose that quantum effects in neural microtubules or other biological structures play a role in conscious experience. None of these is confirmed. None can yet make precise, testable predictions that distinguish it from alternatives. The hard problem of consciousness, why there is something it is like to be a conscious system rather than simply information processing without inner experience, remains as intractable today as it was when David Chalmers formalized it in 1995. We are therefore in the position of being conscious entities, using consciousness to try to understand the universe, while simultaneously not understanding what consciousness is or how it arises from the physics we describe. The tool we are using to investigate reality is itself incompletely understood. This creates a strange reflexive uncertainty. We cannot be fully confident in our scientific framework until we understand what generates the understanding. Whether this is a solvable problem or a fundamental limitation is one of the deepest open questions in all of human inquiry. The universe is approximately 13.8 billion years old. For most of that time, it contained no entity aware of its own existence. For the most recent several 100,000 years, a small number of curious bipeds on one planet, around one unremarkable star, have been developing tools to understand the nature of reality. In the last few hundred years, they have made astonishing progress. And in the last few decades, their instruments and theories have reached sufficient precision to reveal that the map they have drawn, as good as it is missing something large. 95% of the universe is uncharted. The two best theories they have are incompatible at their foundations. The most fundamental features of their experience of reality have no explanation in their best physics, and the anomalies are multiplying as the measurements improve. This is where we are. This is the actual state of knowledge at this moment. Not a comfortable resting place of finished science, but a frontier of genuine mystery backed by precise data. The questions ahead of us are harder than the questions behind us, and the questions behind us produced relativity and quantum mechanics, and the Standard Model, and the mapping of the entire large-scale structure of the observable universe. What lies ahead of us, we cannot say. That is what makes it worth finding out. Consider what the next 50 years of measurement might reveal. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will survey more of the sky in a single observation than the Hubble Space Telescope did in its entire operational lifetime, with a specific goal of mapping dark energy's behavior over cosmic time. If dark energy is evolving, this telescope will detect the signature. The Square Kilometre Array, a network of radio telescopes under construction across multiple countries, will map the distribution of hydrogen across vast volumes of the universe and probe the large-scale structure with unprecedented resolution. Hydrogen is the most common element and traces the underlying distribution of matter, including dark matter. So this survey will constrain theories of structure formation in ways nothing before it could. The Laser Interferometer Space Antenna will listen for gravitational waves from supermassive black hole mergers occurring over billions of years of cosmic history and from the inflationary epoch itself if the signal is strong enough. A detection of primordial gravitational waves would open an entirely new window onto the first fraction of a second of existence. Neutrino observatories deep underground and under ice are accumulating data on the highest energy neutrinos arriving from distant astrophysical sources, probing both the sources and the properties of neutrinos themselves. And particle colliders, including proposed future experiments at higher energies than any currently operating machine, may finally produce direct evidence of dark matter particles or of the physics responsible for the matter-antimatter asymmetry. Each of these instruments represents the culmination of decades of engineering, scientific planning, and international cooperation. Each is designed specifically to address questions that current data cannot answer. Each carries the possibility of producing a result so unexpected that no current theory accommodates it, forcing a fundamental revision of understanding. The history of science suggests that the most transformative results are often not the ones the instrument was primarily designed to find. The cosmic microwave background was discovered accidentally by engineers calibrating a communications antenna in New Jersey in 1964. Cosmic acceleration was found while astronomers were trying to measure how much the expansion was slowing down. Pulsars were discovered as a puzzling regular signal that researchers initially and briefly considered might be an artificial transmission. The universe has a habit of revealing its secrets through channels we did not anticipate. The instruments being built now will almost certainly find something. The question is what? We are, for all our apparent smallness, in a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, the part of the universe that has become capable of studying itself. The atoms in our telescopes came from the same stellar processes as the atoms in the stars those telescopes observe. The mathematics we use to describe curved spacetime is a product of brains that are themselves configurations of matter evolving within that same spacetime. There is something remarkable, possibly profound, and certainly not yet understood about a universe that produces conscious observers capable of asking why it is the way it is. Whether that has meaning beyond the interesting contingency of our existence is a question that physics alone cannot answer. But the investigation continues. The measurements accumulate, the contradictions sharpen. And somewhere in the intersection of all of it, the actual nature of reality waits. Strange, vast, indifferent to our preferences, and not yet fully understood. That is where we are. And it is exactly where the most interesting work remains to be done.